All right. Hi, everyone. I'm Lily Schroeder, and I've been working with Dr. Ali Bangura for the past summer. And we have been researching using cantilever resonance to measure low temperatures in field. So I'm going to take you guys through that today. Um, so to start, why are we researching this? Currently, most low temperature thermometers are resistance-based thermometers, which makes sense. As you can see here, resistance is highly sensitive to temperature at low temperatures. But at the MagLab, we are measuring in magnetic fields, and because resistant thermometers have electrons, they are affected by magnetic fields. This graph here shows the deviation from the expected temperature to the actual measured temperature. And as you can see at 2 Kelvin, which we're looking at low temperatures, this deviation can be as high as 5%, which causes things like this. This is at about 600 millikelvin. And this is the thermometer in a magnetic field. And you can see there's a high variation with the magnetic field, and it also varies differently. So it's not predictable, and it's not a great way of measuring. But there are other ways to measure temperature. And one that we're looking at is not resistance, resonance. We are looking at resonance frequencies, and I'm sure many of you have seen resonance anywhere. Like if we have crystal glasses and you circle the rim, you can get it to sing, or using tuning forks, which is a great example because the cantilever that we are using looks a lot like a tuning fork. This is our cantilever here, and it's basically used like a tuning fork, except we send electrical currents through it to get it to oscillate, and we measure these oscillations with a resonance peak. This resonance peak has two main properties. The G here is the frequency at which it resonates, and the W is the width of the peak. And that's what we're interested in because the width of the peak tells us about the medium that the cantilever is in. And so when it's in a liquid, the cantilever can measure the viscosity of the liquid. And so if we're trying to measure temperature, we want something that viscosity is dependent on temperature, which is in this case helium-3. You can see in this graph, its viscosity is highly dependent on temperature. So when we use this cantilever, we can measure temperature through viscosity. So we've tried this technique on many different cantilevers. Here is one of our early trials with a cantilever that had a quite large width, about 250 hertz. And that caused a lot of noise and just not very accurate readings. So it didn't tell us a lot. Here we had a cantilever with a smaller resonance width, about 10 to 30 hertz, which was great, but I'm sure you can tell there's a curve here. It did end up being dependent on the magnetic field because unfortunately there was some sort of magnetic residue on the cantilever. But that being said, it did tell us stuff. As you can see, these two lines are at different widths, and that's because the higher line is at about 580 millikelvin, and the lower line is about 1.18 Kelvin. And so this alludes to a temperature dependence of these cantilevers, which is really promising. That's what we're looking for. And so, like I just said, that is a promising thing, but we found that we need a really narrow resonance width to get these accurate readings. We don't want all the noise that we found on our first trial on the last slide. So really what we're looking to do is do more trials with different cantilevers and maybe find a cantilever that has a super narrow resonance width to get more accurate readings. But if we do this, we'll hopefully be able to accurately measure temperature in field at low temperatures. And this could, lead to us doing temperature sweeps with magnets, which isn't really done right now. So that could open up a whole new field of research. So thank you guys so much for listening. But yeah, that's my project.